Washington State University. Go Cougs!
In this module, we will continue our discussion of behavior analysis from ambient sensor data by talking about activity discovery. Recall that in the previous modules, we looked at different aspects of activity learning, including extracting features from windows of sensor data collected from ambient sensors. Each one of those feature vectors constitutes a data point that we can use for activity recognition. And in this module, we will use those data points for discovery of activity patterns. In the next module, we will talk about how to use them to predict occurrences of specific activities. When we introduced the notion of activity learning from ambient sensor data, we showed this video of a person entering her home and putting away groceries. But what if we didn't know ahead of time what activities she was performing, or we didn't have any ground truth examples of what the sensor data would look like for these activities from which to learn a model to automatically recognize these activities? Then it would be helpful to automatically discover these activity patterns and from that begin to track them over time. So let's talk about some possible reasons for automatically discovering activity patterns from ambient sensor data. First of all, there may be no available ground truth labels. Many times we put sensors in an environment, we collect the data, and then we want to start analyzing it. The person that lives there may not be providing labels for us. All we have is data, and yet we still want to be able to understand the activities, to track them, and look for changes in a person's routine. Automatic pattern discovery can help us with that. We might want to find inherent patterns rather than focusing on activity classes that are predefined. Let's let the data do the talking and see what kind of repeatable routines and changes in routines occur based on the data itself without predefined activity classes. Predefined activity classes may not make up all of a person's behavior, and we want to model all of it. So we need to perform discovery either on all of the data or at least on the part that is not falling into predetermined activity classes. Recall from our module on activity recognition that predefined classes only make up a portion of a person's day. This graph shows amount of time spent on various activities based on ambient sensors that are put into a set of homes. So we can see that there are a number of activity classes that would be commonly tracked if we were interested in looking at a person's routine for health, for home automation, or other similar purposes. But even though there's a number of activities that are tracked, the other category, comprising all the activities not falling into these predefined classes, makes up about half of the data. So we're not getting the insights that we would hope to gain from the remainder of their routine in this way. In addition, recall that with machine learning algorithms who are trying to optimize recognition accuracy, having such a skewed class distribution will actually affect performance because they will tend to put data points from other classes into the majority class, in this case into the other class, and not perform recognition on the other categories as well as they would if the distribution was more uniform. This graph is based on smart home data or data from ambient sensors put into everyday environments. If we want to look at a broader scale, we can consider the American Time Use Survey, in which Americans are interviewed to determine how they spend their time. What we have here are very common activity categories and the amount of time that Americans on average spend in terms of minutes per day on these different activities, including eating, grooming, cooking, shopping, household chores, cleaning, phone calls, taking care of finance and legal issues, and performing laundry. These are activities that would commonly be analyzed and tracked, as indicated by the fact that they were included on this survey. In fact, these activities fall into well-known categories. There are activities of daily living, or ADLs, that are very commonly tracked and analyzed for a variety of purposes. And what we see in this chart falls into these categories. Eating and grooming are basic ADLs, or basic activities of daily living. Those activities indicated by blue fall into a category called instrumental activities of daily living, and they typically are routine activities that involve manipulation of an object. So from the time use survey, we see activities of daily living represented and instrumental activities of daily living represented, and those are two predefined activity categories which are standard for analyzing a person's routine. So we can group them into those two categories and even add from the time use survey two other specific activities that would be common for analysis from sensor data. One would be exercise. The amount of minutes spent on average per day in exercise is 18. And sleep. The amount of time spent on sleep is 527 minutes per day on average. So if we consider those categories and we put it into a pie chart to look at how much time people are spending on various activities, it would look something like this, where on average people spend 119 minutes per day on basic ADLs, 176 on instrumental ADLs, 18 minutes per day on exercise, 527 minutes on average for sleep, but that still leaves almost half of their daily routine unaccounted for in another category. We know that we do want to look at automatic discovery of activity patterns. We will, in this module, look at two techniques for doing this. One is clustering, and the other is discovery of frequent sequences or sequence patterns in the sensor data. We'll start with clustering. A very common algorithm for clustering is known as k-means clustering, and this is described in greater detail in the machine learning course as part of this program. But we will review it here. In k-means clustering, we are partitioning instances or data points into k non-overlapping or disjoint sets. So we're grouping our data in such a way that each group could represent a different activity class. Recall that our data points in this case are the sensor data, the sensory events that are collected, and in our feature extraction module, we described how we might actually move a sliding window over the data and create a data point out of all the information contained within one window or subsequence of sensory events. So we partition the data points into k sets. So k is predefined, the number of sets that we're looking for, and every set has a representative instance or data point, which we refer to as v sub I for the ith set or cluster. In the clustering algorithm, we put each data point or instance x into a set I such that the distance between the data point and the representative is minimal over all possible sets into which the instance could be put. Then we choose a new central or representative data point for each set and repeat until those points converge. So again, how the clustering algorithm works is that we start with n data points. We predefine k, the number of clusters that we're looking for, and we randomly choose our representatives for each cluster. So k, randomly chosen data points. We assign all the remainder of the data points to the cluster depending on the distance between the data points and the cluster representatives. They go to the cluster with the smallest distance. Once all data points are assigned, we recompute the representative or central location for each cluster, and then we reassign the data points because some may move once the center is recalculated. And this process continues until some convergence criteria. It could be a specific number of iterations through this process, or it could be minimal number of moves of data points from one cluster to another. We will let the Icons represent which cluster a data point is currently assigned to, so these small points are one cluster and these larger circles are another. And these clusters were assigned based on the initial two randomly chosen cluster centers, which are the two dark X's. So once these 2 points are chosen, you can see that the small dots are closest to this X and thus belong in that cluster, while these circles are closer to this X and thus are assigned to the second cluster. Once these assignments are made, we can recompute the center of each cluster, which will likely move from the original X locations and look something like this. So now here's the new center of cluster 1 and the new center of cluster 2, and all the data points are reassigned based on these new cluster centers. With this reassignment, we can adjust the cluster centers again. Now they look something like this, and not only are we seeing movement for each data point from one cluster to another, but we're seeing a little bit more of a balance in terms of equal cluster sizes between the two choices. And after 3 iterations, it has gotten very close to converging. There's not been a lot of movement for individual data points after the second iteration to the third iteration, so that might be a good time to stop. In terms of clustering our activity data, we can consider that every one of those feature vectors that we've created would be assigned to one of these clusters, and that cluster now represents a class of activities. When performing k-means clustering, there is a choice to make, specifically your value of k, which in our case will represent the number of activity classes that we're going to divide the data into. We may have an idea ahead of time of what we want k to be, the number of activity classes that we want to divide a routine into, or we could choose this statistically by trying several choices of k, anywhere between 2 and the number of data points n. And we could settle on the value of k that minimizes the intra-cluster distance, or the distance between points in the same cluster, while maximizing the inter-cluster distance, or the distance between data points in separate clusters. Once we have partitioned all of our data into these different clusters, then we can use it for activity modeling. We can apply the clusters to all of the data and thus divide up all of the sensor data into clusters in order to better understand a person's routine. Or we can just apply clustering to majority classes, such as the other class, in order to decompose it into smaller subclasses that help us to better understand the details within that large class and to provide more of a uniform class distribution for automatically recognizing activities using machine learning techniques. Once the clusters are defined, then for any data point, cluster membership is determined by the distance to the cluster representative. So activity labeling can be automated from the clustering that results. Keep in mind, though, that our data points are determined based on the sliding window that we move over the data, and ultimately it's those data points that will be clustered. Therefore, the window size is actually going to determine the length of the activity. Recall this set of sensory events that was collected from our home, and this corresponds to the sensory events that are generated when our resident performs the activities in the video that we saw. When we were extracting features from the data, we moved a sliding window over the data and extracted features or information that described all of what was going on within the window. So each of these blue boxes might represent a window of data, and the corresponding feature vector is shown on the left. V1 is a set of feature values corresponding to the first box. V2 is a set of features corresponding to the second box. So it is these data points that we will be clustering. While the choice of k is one parameter that can influence the outcome of a clustering algorithm, the other is the notion of distance. Ultimately, we're going to assign a data point to a cluster based on the distance between the data point and each of the cluster representatives. So how are we going to compute distance? One possibility is by using Manhattan distance, which is the sum of the absolute values of the differences between each of the features in the vector. So in this case, the Manhattan distance between the first window and the second window's feature vectors will be the sum of the absolute values of each of the differences in our comma-separated set of values. Specifically, the difference between 8 and 27, 53 and 53, 4 and 4, 11, 11, and so forth, as is shown in this formula, and is expanded out as this sum, which is a combined distance of 579.2. Assuming that the feature vectors have equal length for all of our data points, we can now determine the distance between any two data points in our set to be used for clustering.